Hello, this is Professor Kuehn. In my last lecture, I talked about collisions and considerations of the conservation of momentum. In particular, we looked at a collision between two balls, one moving to the right with a speed of 2 and one moving to the left with a speed of 1. The momentum before the collision was +3, meaning 3 units of momentum to the right. The puzzle that was brought up was that the law of conservation of momentum alone does not uniquely determine the outcome of this collision. So for example, in our after 1 scenario, over here on the left, both balls are moving to the right, stuck together, with a speed of 1. And in that case, the momentum after the collision is +3. But also, in my second scenario, when ball 2 is sitting still and ball with mass 1 is moving to the right with a speed of 3, again, the momentum after the collision is 3. And in our third situation, where the ball with a mass of 2 is moving to the left with a speed of 2, and the ball with a mass of 1 is moving to the right with a speed of 7, once again, the momentum after the collision is 3. That is 3 units of momentum to the right. So the puzzle that we brought up last time was that, again, there's not a unique solution to this problem. So how do we solve this problem? How do we figure out what actually happens in nature? And in order to figure this out, we need to consider something besides momentum. We need to consider the kinetic energy. In particular, is the kinetic energy conserved during this collision? So let me go through and explain these collisions in terms of kinetic energy for each of these cases. So the kinetic energy, or the energy of motion of an object, is equal to, if the momentum is mass times velocity, the kinetic energy is 1/2 the mass times the velocity squared. So in the case of when we're considering what happens before the collision, what is the total kinetic energy of this system of two balls before the collision? Well, it's the kinetic energy of ball 1, which is 1/2, well, let's start with this one, ball 2, 1/2 mass 2 times the velocity of 2 squared, plus 1/2 the mass 1, velocity 1 squared. And what is the kinetic energy? Well, mass 2 is 2, velocity 2 squared is 4, so 4 times 2 is 8, divided by 2 is 4. And what is the kinetic energy of ball 2? Well, the velocity squared is going to be 1, the mass is 1, and so the kinetic energy of ball 2 is 1/2, and so the kinetic energy of this entire system of particles before the collision is 4.5. And the units of this, by the way, are joules. Mass is in kilograms, velocity is meters per second, so 1 joule is 1 kilogram meter squared per second squared. Okay, now what's going on in each of these collisions? What's happening to the kinetic energy? We already know that the momentum in every one of these outcomes is conserved. What about the kinetic energy? Well, the kinetic energy after the collision, in case 1, once again, is 1/2 the mass of the second ball squared times its velocity squared, plus 1/2 the mass of the first ball times the velocity of the first ball squared. And, well, both of them have a velocity of 1, so take 1 squared times 2 is 2, divided by 2 is 1, plus 1 squared is 1 times 1 is 1, divided by 2 is 1/2. So we see that after the collision, there are only 1.5 joules of kinetic energy. What happened to the 3 joules of kinetic energy? Well, in this case, we say that this is an inelastic collision because some of the kinetic energy is not conserved. In particular, some of the kinetic energy is turned into thermal energy. That is, the energy of motion, the kinetic energy, is some of it going into heat or thermal energy. When these balls stick together, the atoms inside of them vibrate, and that is manifested as heat. So these balls are warmer than before. So this is a possible outcome. And in fact, if you put gum between these balls and they hit and they did stick, or some other means of sticking together, you would find that the momentum after the collision is 3, and yet the balls, if you could detect them, would be a little bit warmer because some of the kinetic energy has turned into heat. What about case 2, the kinetic energy after the collision? Once again, 1/2 mass 2, velocity 2 squared, plus 1/2 mass 1, velocity of 1 squared. Here, ball 2 has 0 speed after the collision, so it has 0 kinetic energy. Ball 1 has a speed of 3. 3 squared is 9. 9 times 1 is 9, divided by 2 is 9/2, or 4.5. So this collision, there are 4.5 joules of kinetic energy after the collision. So this, by the way, is what we would call an elastic collision. An elastic collision is one in which kinetic energy is conserved. It is really an idealization. In any practical collision, the kinetic energy, some of it is going to turn into heat or sound, but in an idealization where you have a perfectly elastic collision, this kinetic energy will be the same before the collision and after the collision, and that's what's happening in case 2. What about the kinetic energy afterwards in case 3? Once again, 1/2 mass of ball 2 velocity squared, plus 1/2 mass of ball 1, velocity 1 squared. Well, here, this one has a speed of 2, so 2 squared is 4, times 2 is 8, divided by 2 is 4. So that one has a kinetic energy of 4. And ball 1, well, the velocity is 7. 7 squared is 49, times 1 is 1, divided by 2 is 49, divided by 2, which is what? 48, well, 48 divided by 2 is 24, so it's 49 divided by 2 is 24.5, right? So the total kinetic energy after the collision is 28.5 joules. So apparently this collision, although it's consistent with conservation of momentum, there is more energy coming out of the collision, at least more kinetic energy coming out of the collision, than the kinetic energy that went into the collision. This would be another case of an inelastic collision. That is, the kinetic energy is not conserved. Is this a completely unrealistic collision? After all, where could this kinetic energy have come from? Well, this kind of thing happens all the time. So imagine if these two balls, when they're approaching each other, you were to put a little bit of dynamite on the front of each ball. And when they hit, the dynamite explodes and they go flying apart. What's happening in that case, the dynamite had some chemical energy stored in the bonds between the atoms. And when they strike and ignite, that chemical energy is turned into energy of motion, or kinetic energy. So there must have been something like 24.5 joules of chemical energy that was, 24 joules of chemical energy that was released into kinetic energy. So that's a realistic kind of collision. Okay, so the point of this discussion is that unless you have additional information, it is impossible to tell the outcome of a particular collision event. In the laboratory, when we did this, we made things kind of simple. We had them collide and stick together. And so we found experimentally the outcome was this, and we had the case of an inelastic collision in the laboratory.